Hello all, welcome back to this video on Hamiltonian cycle algorithms. So, what is a Hamiltonian cycle? It's a path in the graph that visits every vertex exactly once and returns to a starting vertex. For example, I have vertices in the graph like this. And this is my start vertex, and my graph goes like this, like this, like this, and again comes back to the same vertex. So this is Hamiltonian cycle. Okay, so what is a Hamiltonian cycle is? A Hamiltonian cycle is a path in a graph that visits every vertex exactly once and returns to the starting vertex, forming a cycle. So this is the example. So what is the goal? To figure out whether such a cycle exists in a given graph or not, and if it does, find the path. So what is our goal is to figure out whether such a cycle exists or not. Goal is to figure out whether Hamiltonian cycle exists in the graph or not. Whether Hamiltonian cycle exists in the graph or not. If exists, we will find the path. Okay, but there is a twist. It is challenging because Hamiltonian cycle problem is a NP problem, as we have been discussing in the previous videos. What is NP complete problem is non-deterministic polynomial time. Non-deterministic polynomial time problem, because this does not have any specific or what we say optimal solution for an algorithm. Okay, there is no fixed or specific solution for the algorithm, for this algorithm. So the problem is NP complete. So no known efficient algorithm solve all the cases quickly. Okay, point to be noted. That's why we often rely on backtracking or heuristic methods. So backtracking, we are well known about it. And what is heuristic methods? Now we'll look into what is heuristic methods. Heuristic methods are problem solving methods that use practical, efficient, but not necessarily optimal approaches to find solutions. Heuristic methods are practical, sometimes efficient, but not all the time optimal solutions. Okay? Especially when dealing with complex problems or limited sources. Okay, when dealing with complex problems or limited resources. They rely on rules of thumb. So heuristic methods rely on thumb rules, educated guesses, and experiences to quickly arrive at good enough solutions. So what does heuristic methods use? They use thumb rules and educated guesses and experiences to find a good enough solution quickly. Okay. So these heuristic methods are often used in artificial intelligence. Where are these heuristic methods are used in artificial intelligence, computer science, engineering, and even human decision making. Human decision making also heuristic methods are used. So I hope there is a good enough understanding about heuristic methods now. We already well know about backtracking, and now we have good enough knowledge of heuristic methods that this follows a practical or efficient but not always optimal solutions, and this method is used when there are complex problems and limited resources, and heuristic methods mostly rely on thumb rules, educated guesses and experiences to find good enough solutions quickly. So where are they regularly used? In artificial intelligence, computer science, engineering, and human decision making also sometimes. Now, going through the algorithm. How does the algorithm of Hamiltonian cycle works? So we'll start with a vertex named vertex 0. Take my previous example, initial example. This is my V1. So we'll start, sorry, this will be my V0, V1, V2, so on. V2, so on, Vn. So we'll start with V0, start at a vertex usually V0 and add it to the current path. We'll add this to current path. Okay. Next, we'll go to the next step, explore the adjacent vertex V1. We'll check whether it is already in the path or not. Check whether already exists in the path. If it already exists, we'll prune that or backtrack that. If it does not exist in the path already, we will add it to the current path, and again we'll go to the next path, and again we'll check if that vertex is already in the path or not, already in path or not. If it is in the path, we'll backtrack it and we'll go to the next vertex. If it is not in the already existing path, then we'll add that vertex. So on, we'll complete till Vn, and again we'll check with V0. Until Vn we'll go and we'll check with V0 also. If there is if the path is connected, that is, we'll recursively move forward if all the vertices are included and there is an edge back to the starting point. So we'll follow this recursive operation till Vn, and there is an edge back to the starting point. This is called edge back to the starting point V0. Then bingo, we have a Hamiltonian cycle. Okay, this is called edge back. Vn to V0 is called edge back. So after reaching to Vn, we will check whether there is an edge back to the start point, that is V0. Then it's a bingo, we have a Hamiltonian cycle. Okay. So the pseudo code explains the same thing. So what are the key points? The is-safe function, here also we use is-safe function, same as graph coloring. Same as graph coloring. Okay. The EC function ensures us only to add valid vertices. Add valid vertices. EC function ensures we add only valid vertices and not already in the path. Not already in path. Okay. The algorithm recursively explores path and backtracks when needed. So what does the algorithm do? It explores all the paths recursively and backtracks when it's not correct vertex, and also whenever needed. Okay. And next, it either finds a valid Hamiltonian cycle or confirms that one does not exist. This algorithm confirms that whether there is a valid Hamiltonian cycle is found or there is no Hamiltonian cycle. It returns true once a valid Hamiltonian cycle is found, and it returns false if none exists. Okay. This method might be fast, this method might not be fast for larger graphs. This method is not fast for larger graphs, but it efficiently captures the logic and complexity of the problem. Efficiently captures logic and complexity of the problems. Okay. What is the key takeaway? That this method is not fast for larger graphs because it has to check each vertex and find the path, but it efficiently captures the logic and complexity of the problems. Thank you.